Hello everyone, and welcome to 7.4, where we're going to learn a little more about how to shift the CG on an aircraft and what those limits are. In our previous lesson in 7.3, we learned a little bit more about weighing procedures and calculations and how to calculate the center of gravity. I'll remind you that the center of gravity is equal to total moment divided by total weight. And you may remember that we did IWAM charts, item, weight, arms, and moments, and essentially we were given information about the aircraft based on what happened when it was weighed. We were able to put it into a chart and figure out where that center of gravity or that balance point is. Now, we've talked about this before, but the center of gravity does change based on weight you put in the aircraft and where you place it. So because of that, one thing that we need to start exploring here is what happens when we change that weight and change that shift. We know in theory that the CG is going to change and it's going to shift, but by how much, and will it be within operational limits? So that's essentially what we're going to be doing today. And I got two videos ready for you. This will be the first two where we discuss those changes. So I'm going to start right off the bat with a problem. An aircraft with an empty weight of 2,100 pounds and an empty weight center of gravity of 32.5 inches after the datum was altered as follows. You have two 18-pound passenger seats that were located at Station 73 removed. You have structural modifications that were made at 77, increasing the weight by 17 pounds. You have a seat and a safety belt weighing 25 pounds that were installed at Station 74.5. And radio equipment weighing 35 pounds was installed at Station 95. Now we need to figure out the new empty weight center of gravity. So I already filled out an IWAM chart for you with the relevant information. Again, the two 18-pound passenger seats add up to be 36, but since they're being removed, we're going to have a negative weight there. We're also going to assume that the datum is at the nose, which means that all of our arms are going to be positive. So this should be the setup for that. What I'd like you to do is take a moment, pause the video, and write this chart down. Once you've done that, then we're going to go over here and start solving this together. So what we have over here, again, this is the same problem that I presented you with. We're going to start filling out this IWAM chart together as a team. And why don't you go ahead? You now know how to do this. Let's calculate all the moments, and let's get a total weight and a total moment. Go ahead, pause the video, let's do that. Thank you for doing those calculations. If you followed along and did things the way that I've taught you in the previous lesson, you should have the following moment readouts as you see on your screen, and a total moment of 72,131 with a total weight of 2,131. Now go ahead, divide the moment by the weight, and let's figure out our center of gravity. Okay, thank you for doing that. If you did the calculations correctly, your empty weight center of gravity should be somewhere in the neighborhood of 33.7. So again, you're going to notice that our original arm, or our original empty weight center of gravity was 32.5. But now that they've made all these adjustments, we need to calculate a new empty weight center of gravity because this stuff causes the center of gravity to shift backward. You add more weight backward, the center of gravity shifts backward. There seems to be a connection there. So now that you've added all this material, you're left with 32.5 over here, and you're left with 33.7 over here. All this information shifts your center of gravity back by about 1.2 inches. Again, an inch and a quarter doesn't seem like a lot, but believe it or not, it actually makes a huge difference in an aircraft loading scenario, especially when often your center of gravity on airplanes like this, your range can be maybe 10 to 12 inches. So we're going to go over, do another problem, and this one should be faster than the last one now that you're starting to get the pattern here. This is going to be very similar to the previous problem, but I've made a couple of changes here. We have an empty weight of 1,800 pounds, EWCG at station 31.5. The passenger seats are now 15 pounds each, so that changes our weight to -30 instead of the -36 from before. With an arm at 72. The structural modifications are now 14 pounds at arm 76. The seat and safety belt are now 20, and the arm's at 73.5, and the radio equipment is 30 pounds and was installed at station 30. So now that you have that, here's your IWAM chart. Take a moment, pause the video, write it down, and then let's go ahead and get this done. Thank you for knocking out those calculations. Again, to get the moment, you do weight times arm is equal to moment. So I multiplied across right here and got the following values for the moments for each of the following items. When you add all these together again, weight times arm is moment, weight times arm is moment, you get the idea. When you multiply these together and get these values, you add them together, and that sum of the moments is 57,974, and the weight is 1,834. Go ahead, divide those two values and figure out your new empty weight center of gravity. Thank you for doing those calculations. If you took your moment divided by the weight, your new empty weight center of gravity is 31.6. Compare that to 31.5. By adding all of these changes, you shifted your center of gravity back by 0.1 inches. That balance point is now shifted because you added weight. Okay, we're going to do one more variation of this. Again, that'll be problem number 3 in the slideshow here. And here's the situation. Again, we have an aircraft that are 1,500 pounds at arm 28.4. These passenger seats are now 12 pounds each, so again, a weight of -24 because they're being removed at arm 68.5. You have structural modifications that are 28 pounds at arm 73. You have seat belt setup that's 30 pounds at arm 70.5. And you have radio equipment that weighs 25 pounds installed at arm at station 85. So with that, take a moment. I want you to copy down this IWAM chart, and let's go ahead and do the calculations. Thank you for completing those calculations. If you complete them the way that you were supposed to, the answer that you would have gotten, again, you're multiplying weight times moment here, so you have 42,600 over here. You go down the line doing the same thing, weight times arm equals moment. And once you do that, your sum total of the moments should be 47,240, and your sum of the weights should be 1,559. Go ahead, divide those two, and let's get yourself the new empty weight center of gravity. Okay, so by making these modifications, your new empty weight center of gravity is now 30.3. Contrast that to the original empty weight center of gravity at 28.4 inches after the datum. And what you're going to notice is that by making all of these modifications to the aircraft, that balance point has now shifted back about 2 inches. So again, pretty significant change. So now that we've done that, and we have a basic idea of how weight shifts the center of gravity, I want you to be familiar with something called ballast. We've mentioned the concept of ballast previously in lesson 7.2, but in case you've forgotten, ballast is essentially when you're adding weight to the airplane to better balance the airplane. Like, for example, if you have an airplane that has a center of gravity that's too far forward and it tends to lean forward, then you might, to balance it like a seesaw, want to toss ballast or extra weight in the back to compensate for that. There are basically two types of ballast. The first type of ballast that you'll notice here is that you have permanent ballast that's installed in some aircraft where they'll literally install weight plates inside of the aircraft. They do this in cars. They do it in a number of places to make sure that vehicles are balanced. This isn't just an aviation thing. Now, that's called permanent ballast. In the case of needing ballast and it's more temporary, very often what they'll do is they'll toss sandbags in the aircraft, and it essentially has that same effect. They'll tie down sandbags somewhere in an aircraft, so that way they have a temporary fixed ballast that does that. Now, if you have an aircraft that's out of the CG range, the operating CG range, and you need to make those changes, then what you're going to do is you're going to take that, you basically have to figure out what your current center of gravity is and what it needs to be. What's that derived CG and what is that required CG? Once you know that, you also need to figure out what the arm is, like where you're going to place that ballast and what that distance is to the datum. And you also need to figure out, well, that's basically all you need. Once you have all that information, you can plug it into this magical formula right here, and it's going to tell you how much ballast you need to either put on or take away. If you're taking away ballast, then this number is going to be negative, like if you need to reduce the weight. But if you need to add weight, then this ballast number will actually turn out to be positive. So how about we do one of these calculations together, and then once we're done doing one of these calculations together, I'll have you do the next one on your own. So going into this, again, ballast, very important here. We have an aircraft that weighs 4954 pounds. That's the derived weight right here. And it has a center of gravity of 30.5 inches, which is the derived or actual CG. However, since the range has to be between 32 and 41, we need to change the center of gravity and shift it so that way it hits the required CG, which is 32.0 inches in this case, because you want to do the minimum. So you want to do 30.5 is closer to 32 than it is 42.1. So you're going to want to go to that minimum distance. So you have that required CG, you have the CG you actually have, and your job is to find the minimum weight of ballast necessary to bring the CG within that CG range to get it to 32, and you have a ballast arm of 162. So I'm going to do a little bit of mental math here just because of the logistics of trying to get all this to work out. Again, I'm going to assume here that you know order of operations well enough that you can plug these numbers in and do them themselves, but I'm going to run you through my mental process anyway, just because it's a good thing to do. So derived weight is 4954. We plug that in over here. We have a required weight minus our required center of gravity minus our derived center of gravity, which is 32.0 minus 30.5. Mentally, that gives me 1.5 inches. So on the top, I have 49.54, which I'm going to do here on my calculator on my phone. That's 4,954 times 1.5. That's going to give me 7,431 on the top. Now on the bottom we have a ballast arm of 162, and we're going to subtract 32 from that, and 162 minus 32 is going to give me 130 on the bottom. So we have 7,431 on the top, we have 130 on the bottom. You divide the two and you're going to get your required amount of ballast. So you take 7431 and you divide that by 130. And what I get for my ballast is 57.16 pounds. So you have to add an additional 57.16 pounds minimum in order to get the CG range within that 32-inch minimum. So that's basically how you do it. Now why don't you go ahead and do the next one on your own. Thank you for doing that calculation. If you got what I got, then you should have had a ballast of negative 37.2 pounds. That's right, that's negative, and the reason why it's negative, because we're above the limit of center of gravity over here, we actually have to take weight away this time in order to get that 43 down to 42.1. So again, that's going to be negative 37.2 pounds. We're taking away 37.2 pounds from the ballast in order to get it within that center of gravity range. I hope this information was helpful to you. I'll see you in the next video.